Hello, I am Samir. I am a PhD student at University of Illinois at Urbana-Champaign, and I will be presenting our work on testing equality under the local broadcast model. This is joint work with Professor Nitin Vedya at Georgetown University. Consider the two-party equality problem. There are two players, Alice and Bob. Both Alice and Bob start with a k-bit input. They communicate by passing messages to each other. The objective here is that if the two inputs are not equal, then either Alice or Bob must be able to detect the mismatch. Now this can be extended to the multi-party setting. We now have n nodes. Each node has a k-bit input. As before, if all the inputs are not equal, then we want some node to be able to detect this mismatch. So if all the inputs are equal, then we want all nodes to output 0. But if any two inputs are not equal, then we want some node to output 1. The n nodes are connected via an arbitrary communication graph G, so that nodes can only communicate with their neighbors in this graph. Note that we are using n for the number of nodes and k for the input size. The objective in this work is to find protocols for the multi-party equality problem that minimize the total transmission cost when nodes are connected via an arbitrary communication graph G, and they communicate using the local broadcast model, which we are going to define next. In the local broadcast communication model, whenever a node sends a message, it is received identically by all the neighbors of that node. For example, in this case, when node U sends a message M, it is received identically by both of its neighbors V and W. When the communication graph is complete, then this corresponds to the global broadcast model, or the so-called public blackboard model, where a message sent by a node is received identically by all the nodes in the network. However, when the communication graph is not complete, then this is different than the global broadcast model. The multi-party equality problem has been considered before in the point-to-point communication model. To see the difference between the two models, let us look at this example. In the point-to-point model, when a node U sends a message MA to node V, it is private between U and V, and node W does not overhear it. So if node U wants to communicate with node W, node U must send another message MB to node W. And again, this message is private between U and W, so node V does not overhear it. Now the total transmission cost that is paid by node U is the total size of both the messages MA and MB. On the other hand, in the local broadcast communication model, when a node U sends a message M, it is received identically by both V and W. So the total transmission cost paid by node U is just the length of the message M. It does not have to repeat the message again to send to the other node. So there is an asymmetry between the number of bits that are transmitted and the number of bits that are received in the local broadcast model. Node U sent M bits, but M bits were received by both V and W, so in total 2 M bits were received. In this work, we are interested in minimizing the total number of bits that are transmitted in the protocol. In the point-to-point model, a linear program-based lower bound is known. Based on this lower bound, in general graphs, any multi-party equality protocol must have a transmission cost of at least kn over 2. On the other hand, simple protocols solve multi-party equality problem with a cost of k times n minus 1 on any communication graph. These simple protocols correspond to finding a rooted spanning tree. Now each node will send its entire input to its parent. Because the tree spans the entire graph, so if there is a mismatch, then some node will be able to detect it. It is also known that no linear protocol can do any better than a simple protocol. On the other hand, Allen et al. Designed nonlinear protocols which are optimal up to an additive factor in many cases. In this work, we consider static protocols. This is similar to what has been considered before in prior work. In static protocols, the player turns are determined in advance, so we know in each round which player is going to talk. The number of bits transmitted is also independent of the inputs. In essence, we are pre-assigning the capacities to the nodes. Remember that in the local broadcast model, a message that is sent by a node is received identically by all of its neighbors, but the transmission cost is paid only once. So we are assigning capacities to the nodes, not the edges. Since we are minimizing the total transmission cost, so we want to minimize the total capacities that have been assigned to all the nodes. For the lower bound, we follow the same approach as in the point-to-point setting. We take the two-party lower bound and then we extend it to the multi-party setting. In the two-party equality problem, it is known that both parties must share k bits between each other. This can be extended to the multi-party setting by considering two-way partitions of the nodes. So in the multi-party setting, we have that for any two partitions of the node set, the protocol must share k bits between the two parts. By extending the two-party lower bound, we get a linear program for the multi-party equality problem. Under the local broadcast model, the linear program assigns capacities on nodes. These capacities must be non-negative. Furthermore, for any two-way partition of the nodes, we want that there must be at least k bits which are exchanged between the two parts. These messages are carried by the edges that cross the partition, so these must be transmitted by the nodes that are at the boundary of the two parts. The boundary of any part consists of nodes that have neighbors on the other side of the partition. So for every edge uv that crosses the partition, we have that both the endpoints u and v are in the boundary of the partition. So the total capacities that are assigned to the nodes at the boundary of the partition must be at least k, because k bits must be transmitted across the partition. Since we are minimizing the total transmission costs, so we want to minimize the total capacities that have been assigned to the nodes. This linear program is going to be our lower bound for the multi-party equality problem under the local broadcast setting. We first look at simple protocols where nodes either transmit their entire input or do not transmit anything at all. In the point-to-point setting, simple protocols were supported on a tree. Every node transmitted its entire input to its parent in the tree, and these came within a factor 2 of the LP lower bound. In the local broadcast setting, we pick some subset of nodes that transmit their entire input. On receiving messages, nodes check the received values against their own input. We want to pick enough nodes in the simple protocol such that if there is a mismatching input, then some node must be able to detect it. The transmission cost in this setting is k times the number of nodes that have been selected to transmit their input. So we want to minimize the total number of nodes that have been selected to transmit their input. Now in a complete graph, we can just pick a single node, and which would transmit its entire input. That would cost us k bits, and that would solve the problem in the complete graph. In contrast, in the point-to-point setting, we would have needed at least kn over 2 bits to be transmitted even in the complete graph case. In the point-to-point setting, simple protocols corresponded to selecting rooted spanning trees. In the local broadcast setting, simple protocols correspond to selecting weakly connected dominating sets. Now, a dominating set in a graph is a set S such that every node is either in the set S or it has a neighbor in S. Another way to put it is that S is a dominating set if the edges incident to S induce a spanning subgraph of G. For the weakly connected dominating set, we further require that this spanning subgraph must also be connected. So S is a weakly connected dominating set if the edges incident to S induce a connected spanning subgraph of G. In the point-to-point setting, any spanning tree would have been fine, but in the local broadcast setting, we really want the optimum weakly connected dominating set because we want to minimize the total number of nodes that are transmitting. This problem is NP complete. Furthermore, in the paper, we show that simple protocols can cost log n times the LP lower bound. For a quick comparison, in the point-to-point setting, simple protocols were supported on rooted spanning trees. These came within a factor 2 of the LP lower bound, and these were the optimum linear protocols. On the other hand, in the local broadcast setting, these simple protocols are supported on optimum weakly connected dominating sets, but these can be log n times the cost of the LP-based lower bound. In fact, in the local broadcast setting, it turns out that linear protocols also perform better than simple protocols. In the rest of the talk, we're going to construct linear protocols that come within a constant factor of the LP-based lower bound. To construct linear protocols, we will convert solution of the lower bound LP using Reed-Solomon codes. These will be linear protocols that come within a factor 4 of the LP-based lower bound. Again, for contrast, under the point-to-point model, linear protocols did no better than simple protocols. But under the local broadcast model, we are able to show that linear protocols do perform better than simple protocols. Reed-Solomon codes convert k-bit inputs into code words with two parameters m and l. A Reed-Solomon code has m symbols, and each of these symbols is k over l bits long with the following property. Any l out of the m symbols can recover the original k-bit input. Now, for the Reed-Solomon codes to exist, we want 2 to the k over l to be greater than m. So we assume that k is sufficiently large for this to exist, and we are going to choose the parameters m and l next. We start with an LP solution. The LP solution assigns a capacity C of u for every node u. We will normalize this capacity to get weights for every node. So for the weight for node u is y of u, which is just the capacity from the LP solution divided by k. Now recall that k is the size of the input. So these weights are basically the normalized capacities from the LP solutions. We choose m to be the sum of these weights, and we pick l to be half. Now for Reed-Solomon codes, we wanted m and l to be integers. So we multiply both m and l by a factor q, which is chosen to make everything an integer. From the Reed-Solomon code word, each node u is assigned symbols proportional to its normalized weight in the LP solution. Now, even though we are talking about symbols in the Reed-Solomon code word, these are really functions that nodes are going to use to encode their messages. So sigma u in this case is the function for the symbols that were assigned to node u, and node u is going to compute the corresponding symbols in the Reed-Solomon code word from its own input. In our protocols, nodes are either colored red or blue. Red nodes transmit their entire input to their neighbors. So in this example, node u is colored red, so it's going to transmit its input xu to both of its neighbors. Blue nodes, on the other hand, compute their corresponding code symbols on their input, and then they transmit these code symbols to their neighbors. So node V, in this case, is colored blue, so it's going to compute its code symbol sigma V on its input xv, and it's going to transmit these code symbols. On receiving messages, nodes check for consistency of the received values against their own input. So in this example, node W is receiving messages from a red node U and a blue node V. So node W in this case receives the entire input of XU, so it checks if the received value is equal to its own input XW. On the other hand, from node V, it's receiving its code symbols from the Reed-Solomon code word, so node W is going to compute the corresponding code symbol sigma V on its own input XW, and it's going to check that against the received value from node V. Note that node W, to check for consistency of messages received from node V, is computing the code symbols for node V on its own input. So it's computing sigma V on its input XW, and then checking that against the values that have been received from node V. To create our protocols, we're going to color the entire graph either red or blue in rounds. Initially, all the nodes are white. In round 1, we pick any arbitrary node U, and we color it red. Now this node U has some neighbors, and we're going to color those neighbors blue. In a round I greater than 1, we have already colored some of the nodes red and blue. These form the component S. In this round, we are going to pick any neighbors U of S which has not been colored either red or blue. So node U is still white. Now node U has potentially some other neighbors not in S which are also still white. There are two cases to consider here. In the first case, the normalized weight from the LP solution of nodes U and its white neighbors is at least half. In this case, we're going to color the node U red. The white neighbors of U, we're going to color them blue. So in this case, set S expands to include U as well as U's neighbors. In the second case, the normalized weight from the LP solution of node U and its white neighbors is less than half. In this case, we're going to color the node U blue, but we're not going to color its white neighbors. So in this case, set S expands to include U, but not its white neighbors. To prove the correctness of the protocol, consider a round I and the red and blue component S in this round. We show that our protocol solves the multi-party equality problem in the subgraph induced by this set S. We prove this inductively. For the base case, we look at round 1. In round 1, we picked an arbitrary node U. We colored this node U red, and we colored its neighbors blue. So after round 1, the red and blue component S consists of node U and all of its neighbors. Since U is a red node, so in the protocol, node U transmits its entire input. So all nodes in the red and blue component S have node U's input since they consist entirely of node U and its neighbors. So all the nodes in this red and blue component S will compare their own input against U's input. So if there is a mismatch in the set S, then some node will be able to detect it. For the inductive step, there are two cases to consider. We consider each of them separately. In the first case, we had a red and blue component S. We picked a neighbor U of S which was still white. We colored node U red and we colored its white neighbors blue to get the set S prime. Inductively, our protocol solves the multi-party equality problem in the set S. So if there is a mismatch within the set S, then that will be detected by a node in the set S. So by the inductive hypothesis, we can assume that all nodes in the set S have the same input. Now, the neighbors of U in the set S have U's input. That's because node U is a red node, so it is going to transmit its entire input. So if there's a mismatch between input of U and the input in the set S, then that will be detected by some neighbor of U in the set S. On the other hand, if there's a mismatch between node U and any of its neighbors which are not in S, then that will also be detected by the neighbors of U which are not in S. These are the neighbors which were colored blue in this round. So if there's any mismatch within the set S prime, then that will be detected by some node in the set S prime. In the second case, we picked a node U and we colored it blue, but we did not color any of U's neighbors which were not already in S. So S prime consists entirely of set S and the node U that was picked in this round. When we picked node U and its white neighbors did not have a lot of normalized weight from the LP solution. Now, based on the linear program, this implies that the neighbors of U which are in the set S must have weight at least half in the LP solution. Remember that S is colored entirely red or blue, so the neighbors of U which are in set S must either be red or blue. As before, by the inductive hypothesis, we can assume that all nodes in S have the same input. Now, if U has a red neighbor in the set S, then this red neighbor will transmit its entire input in the protocol. So you will be able to detect if there's a mismatch between the input at node U and the input in the set S. So we assume that all of U's neighbors in the set S are blue. Based on the weight of the LP solution, U will receive at least L code symbols from the neighbors in S. So U is able to actually reconstruct this input from these L code symbols that it has received from its neighbors in S because of the property of the Reed-Solomon code word. So if U has a different input than S, U will be able to detect it. Now from this lemma, since for every round I, we know that the protocol solves the multi-party equality problem in the subgraph induced by the set S. So this implies that the protocol actually solves the multi-party equality in the entire graph G. We next bound the transmission cost of this protocol. We consider the red nodes and blue nodes separately. So red nodes transmit their entire input. So we want to bound the total number of red nodes. Based on the coloring process, the total number of red nodes can actually be bounded by 2 times the total normalized weight of the LP solution. Since each red node transmits its entire input, so each red node transmits k bits. In total, the total number of bits transmitted by red nodes is 2k times the normalized weight of the LP solution, which is equal to 2 times the actual cost of the linear program. For the blue nodes, each blue node U transmits Q times Y of U code symbols. These are the total code symbols that were assigned to U from the Reed-Solomon code word. Now each code symbol is K over L bits long, so the total transmission cost of the blue nodes can be upper bounded by K over L times M, where M is a total code symbol in the Reed-Solomon code word. Expanding that, we get K over L times Q times the total normalized weight of the LP solution. We expand L and the two Q's cancel out, so we eventually get 2K times the normalized weight of the LP solution, which is equal to 2 times the actual cost of the LP solution. So in total, we have that the red nodes transmit at most 2 times the cost of the LP solution, and blue nodes also transmit at most 2 times the cost of the LP solution. So the total transmission cost of this protocol becomes 4 times the cost of the LP solution, which is what we wanted. So to summarize, in this paper we have considered static protocols for the multi-party equality problem under the local broadcast model on arbitrary undirected communication graphs. We presented an LP-based lower bound, and we showed that the simple protocols can cost log n times this lower bound. We also presented linear protocols which come within a factor 4 of the LP-based lower bound. Thank you.